degrees Celsius. Then we'll change to steam at 100 degrees Celsius. Okay, so Jonathan, what is the process from water to steam? What's this process?
Boiling.
Boiling, very good. Very good. Okay, so when we talk about boiling, Jonathan, can you tell me why do you say boiling? You don't say evaporation. Your concept is very good. It's perfectly good. Just that I want you to explain to us why you say boiling, but you never say evaporation.
Because heat is not required for evaporation.
Are you sure? No, it's required. It's required. Evaporation boiling, because this temperature, right? 100 degrees Celsius is the boiling point. Very good. Thank you. Boiling point. Okay, so at boiling point, boiling is better. Then after that, temperature increase, right? So basically for each status, right, for the -5 degrees Celsius to 0 degrees Celsius of ice, you use which equation? Cm delta theta Q equals to ml. Okay, so maybe I hear from Gareth. Gareth, first change from ice of -5 degrees Celsius to 0 degrees Celsius of ice. Do you use first equation or second equation?
First equation.
Very good, because there's change in
temperature.
Temperature, very good. Okay. Second change, 0 degrees Celsius to 0 degrees Celsius from ice to water. Do you use first equation or second equation?
Second one.
Very good. Reason?
Because it's changing state.
Very good. Excellent. Thank you. Very good. Okay, so now we look at from water to water at 0 degrees Celsius to 100 degrees Celsius. Let's hear from Rachel. Rachel, for this change, right, from water to water, but temperature change from 0 degrees Celsius to 100 degrees Celsius, do we use first formula or the second formula? There's a change in temperature. Do we use the first one or the second one?
The first one.
Very good. Reason? How to explain?
Because the first one got change in temperature.
Ah, excellent. What about the second change from 100 degrees Celsius water to 100 degrees Celsius steam? Which formula do you like to use? First one or the second one?
Second one.
Excellent. Reason? Reason?
Because the temperature the same.
Yes, temperature is the same, so there's a change in state, change in phase. Okay, so the last one, okay, from 0 to 100, sorry, from 100 degrees Celsius to 101 degrees Celsius, steam to steam. Which formula do you like to use? First one or the second one?
First one.
Very good. Reason?
Change in temperature.
Very good. Excellent. Okay, I'll give you few try. Okay, very good. Okay, so now let's do the question now. Okay, so just a quick check. Have you all printed this out? Or you have, if you have another device, for example, you have a handphone downloaded with class in, you can also refer to it if you don't want to print it out. But I'll suggest you to print it out and do on the do the working on it. Okay. What happened to the connection? Okay, you may start now. The questions. So we'll be finishing these few questions. There are 11 questions here. Then we'll start doing the last part of DC circuit, and we'll continue practical electricity. Jonathan, how is your home-based learning going so far?
It's going okay.
Okay. Do you have a lot of questions from school?
Not really.
Not really. So it's live streaming lessons.
Yeah. For physics, my teacher just started doing DC.
DC. Okay. Thank you. Okay. And how about Gareth? How is your home-based learning so far?
Okay.
Okay. So not much work given yet.
Not as normal.
Normal. Okay. 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 Hi, Chloe. Welcome back. Okay. So we do question 48 first. Okay. Hi, Rachel. Welcome back. Okay. So we'll do 48 first. I don't think 48 is easy. Okay. After you try question 48, I'll go through with you. And I'm going to give you the small drawing board. The small drawing board, so you can write an answer on the small drawing board.
遗忘我觉得 idea 不错，但是因为让家长看到宣传的时候是一目了然的，它有什么内容，还有价格，就像一个所有信息都在一个宣传页上，可否做一个这样的东西呢？我发到我的朋友圈或者是家长群里。你刚才报价的那个金额是新加坡那边的价格还是人民币啊？
You can write down your answer in a short while. Oh, you can already write. I already handed out to the drawing board. Okay, I think I can show you the working. I notice many of you not very sure. Okay, I'll give you 1 more minute to try question 48. Then I'll go through with you. Okay. Okay, so far Gareth did very well. Okay, let me show you the working now. Let's do together. Okay. So class, I'll collect back the drawing board first. I'll do on my drawing board. You can look at the working. So first of all, for this question, we shall think about which formula we want to use. So for calculation question, right, there are two main formula. One is thermal energy, which is also known as heat energy, right? Q is energy. The SI unit for energy is in joule, right? The unit is joule. Okay, Q equals to Cm delta theta, or Q equals to ml. Okay, in this case, because there's a change in temperature, you can see increase in temperature. Okay, increase in temperature. So we shall choose this formula. Okay, you can see on my drawing board, right? Q equals to Cm delta theta. Okay, so we find QP. QP equals to MP CP delta theta P. Okay, and QP over QQ equals to what? What's the ratio? Because it's by the same heater. By the same heater means the power is the same, right? Power is the same power. And in the same time, power multiplied by time, you learn in what energy power equals to energy, which is thermal energy here. So they are the same. Ratio is 1:1. Okay, so then we can do MP over MQ. What's the ratio? Given that the material have the mass ratio 2:1, so the ratio is 2:1, 2/1. Okay, what about the change in temperature? Change in theta P over change in theta Q. Then this is information we can get. The material P increases its temperature twice as much as material Q. So this ratio is 2:1. Okay, so far? So then we can do a bit mathematics here. Okay, so we can say MPCP delta theta P over MQCQ delta theta Q equals to 1:1, because just a substitution. And this ratio is 2, right? This MP over MQ is 2:1, so I can you replace this with 2. 2 times CP over CQ times another, this is also 2 times 2 equals to 1:1. So I can find CP 4 times CP over CQ equals to 1. Therefore, CP over CQ equals to 1:4. So the answer should be A. Okay, A is the answer. Okay, take note of that. 48 is for the question 48 is difficult, but 49 onwards should be simpler. Okay, so you may start question 49 onwards now. Okay, Gareth, do you need to go at 11:30 or no need? So
No need.
because I remember you have another tuition, so it's also online, so you don't need to travel, is it?
Yeah, I start at 2, so I can stand you 1:45.
Oh, okay, understand. Okay, 48 should be 49 should be easier. Okay, so 49. Let me hand out the drawing board again. You can write down your answer. For 49, melting process is change in state, right? So we shall use this formula. Q equals to M times L. And this case is latent heat of fusion. Mass is 2 kg. And the L is given in the question. We do substitution. Gareth, well done. Jonathan, please write down your answer on the board. Rachel, I help you to delete the previous answer. Now you can write down the answer on the board. Chloe, can you understand question 49? Question 4, because you haven't learned much in school. So what is Q? Q equals to M times L. Yeah.
That's an accident.
Oh, okay. So you do the multiply, right? It's basically 2 multiplied by this value to find the heat needed. Okay. Heat is thermal energy. Okay.
Then does melting and boiling make a difference?
Boiling also ml, but for boiling, right, Q equals to M times LV. This is called latent heat of vaporization. Latent heat of vaporization. LF is the latent heat of fusion. So formula wise is the same, but the value will be different. Value is different. Okay. But in both cases we use a formula Q equals M times L. Okay, Rachel did a good job. Rachel did a good job. Okay, trophy for Rachel. Jonathan did a good job. We just do the 11 question, then we'll continue with electricity questions. Okay, we'll just do the 11 MCQ questions and revision for thermophysics. Chloe, if you have any question, you can raise your hand. Okay, raise your hand.
嗯，可能深圳的物价，没有新加坡那么高，所以消费能力可能也稍微差一点点。你们成本再核算一下，看看能不能有一个更有竞争力和更有诱惑力的价格。
Chloe, what's your answer for question 49? Yes, correct. Good. So please try question 50. Jonathan, I'm looking at your question for question 50. Can you tell me how do you get the answer? Just verbally explain to me will do.
Q equals MLV.
Q equals to MLV. Yes. What is the M here?
2.
2. What is the LV? This value.
2260000.
Yeah, so did you multiply? The answer you give me is C.
Oh wait, no, it's D. D.
Yeah, okay. Thank you. Okay, good. Gareth, you don't need to delete your answer for the previous part. You just type out the answer like 49 is what, 50 is what. Okay, save some time now. Thank you. Rachel, let me check Rachel's. Rachel, well done for 50 and 51. Excellent. So, Rachel, your thermophysics okay? Is it? You did quite well. So
Yes.
okay, you did quite well so far. Gareth, well done for fraction 50. Chloe, what's your answer for question 50? Question 50, what's your answer? Do you need help? Sorry, what's your answer?
D.
Yes, good. Excellent. Good. Okay, so class, please continue with question 50. Okay. 50 is more of a concept. 50 is more of a, sorry, 51, man. Question 51. Okay, Chloe, well done for question 51, 52, 53. Oh, Gareth, well done. Jonathan, well done. With 56, Gareth, well done. Rachel, well done for 51 to 53. Oh, okay. Jonathan, 55, good. 56 and 7 are very, very well done. Rachel, I'll delete your working for 51 to 53. Okay, you did very well so far. Since we all did very well so far, next week I will be doing structure questions with you on thermophysics. Okay, Rachel, well done for question 54. Chloe, do you need help for the subsequent questions? Which question you need help with? 50.
Everything.
Sorry?
Everything.
Everything. Okay, so you give me a question like 53, 54. Which one you need more help with?
53, I'm okay.
53, okay. 54? Okay. So I'll show you the 54 working. Okay. Chloe, can you see the working on the drawing board now? Yeah. So for 54, what you need to do is to get the various part. Okay, various parts energy. Okay, so for different part, no matter changing temperature or changing state, there's some energy required. 1, 2, 3, 4, 4 parts. Okay, Gareth, have you done? Have you done all the question?
I haven't done 57.
Oh, okay. Okay, continue. So basically, Chloe, you look at the change, right? Sometimes MC delta theta, if that's changing temperature, if changing state, then is ml. Changing temperature from 0 to 100 degrees Celsius, you change times 100 minus 0. Changing state, ml, you'll use the mass times the L. Okay, then you'll find the total energy. Does it make sense? So the key concept is there any change in temperature or state? Change temperature, we use Cm delta theta. Okay, if we change state is ml. That's all. That's 54. Gareth, 58, your answer is not correct. Please try again. 58, the answer is not correct. Okay, Jonathan did a very good job. Jonathan, everything correct. Excellent. Okay, Jonathan, you can take out, since you have done everything, you can now take out your worksheet on DC circuit given last week. Is it this one? No, not this one. The other one. This one. Have we finished every questions here? Do you remember? You stop at one of the question. I remember question 4. You start question 4, right? You can continue the rest of the questions. Which question did you stop at? Which question did you stop at? current electricity AC circuit worksheet is how it looks like.
I think we stop at question 5A.
Okay, you can continue the rest of the question now, since you have done the thermal revision questions. Okay. Chloe, which question you are doing now?
55.
55, okay.
No, I don't know how to.
You don't know how to do. Okay, for 55, right? So, I will show you the solution here. Okay, this is a working. Basically, the temperature 55, the temperature is at 90 and 40 at first. They should, because they are put together, so they are in thermal contact. They are in thermal contact. So they have the same final temperature. Same final temperature. So for the, so Chloe, you look at the board. So there's a gain in thermal energy by the 40 degrees Celsius water, because at first it's at a lower temperature, right? So it gain energy. The other one at a higher temperature will lose energy, lose temperature, right? So the final equation you should form is this. So the gain of thermal energy by the 40 degrees Celsius water equals to loss of thermal energy by 90 degrees Celsius water. So you form this equation, then you can get the final temperature. They have the same final temperature eventually. Okay, so it's use a concept m times c times delta theta. Okay, equals to the other m times c times delta theta. Okay, understand? Okay. Gareth, how is the progress for 57 and 58 you have been doing for a while?
I don't know how to do.
57 or 58?
Both.
Both. Okay, let me show you the working for 57. This is the working for 57. Do you see on your drawing board?
Yeah.
So for 57, the 60 degrees Celsius water actually will gain energy, because at first it is at lower temperature, right? This is lower temperature. So it will gain energy. Then the other one is at higher temperature. Okay. So the copper will lose energy until 100 degrees Celsius. Okay. After that, the total energy here is from the copper. So we can use 80,000 joules to change the thermal energy of water from 60 to 100 degrees Celsius. There's still extra 240,000 joules of energy remaining. This remaining energy will convert some of the water to steam, to gas state. Okay, then this is how we do. Okay. Any question?
No.
So you have to find the total energy.
Okay.
Okay, yeah. Rachel, how is your progress? Rachel, do you need help for any of the part? 50?
56.
56. Okay, 56. Okay, Rachel, this is the working for question 56. Okay, question 56. So when the two material of different temperature come into thermal contact, the one with higher temperature will lose thermal energy and the one with lower temperature will gain thermal energy. So they'll reach thermal equilibrium. They'll reach thermal equilibrium eventually. Okay. Okay. Rachel, can you understand the working?
Yeah.
Okay. Okay, Gareth, do you need help for question 58?
I'm trying.
Okay, okay. Chloe, which question you are doing now?
56.
56. Do you need help or you want to try yourself?
Try.
Okay. Gareth, you need help for question 58.
Is it B?
58. D for dog.
B.
B. Yes, correct. That's correct. Good. Excellent. Okay, well done. Okay. Okay, now Gareth, you can go back to the DC circuit worksheet now.
Okay.
I think we finished at question 5, part A last week. We can continue the rest of the questions now. Chloe, how is your progress?
I got 117.
You're doing question 55, right?
56.
56. What is the answer?
117.
117. Final temperature 117. Shouldn't be leh. Okay, I show you the working now. This is the working. Question 56. So basically is the one of them lose energy, like this is loss. So from 120 to a lower temperature, which is T. Very similar to just now the question. The other one is gain energy. So the final temperature should be higher than 40 degrees Celsius. So it's T minus 40. Oops, sorry. Sorry, I accidentally deleted.
Saying 57.
57. Have you tried? What's your answer?
I don't know.
Sorry, none of them. Is it?
Huh?
What's your answer for 57?
I don't know.
Okay. Okay, so let me show you the working for 57. This is the working for 57. So basically the energy, right, from the copper can release this much of energy when it cool down to 100 degrees Celsius. And for the water, it only gain 80,000 joules. So there's still 240 joule of energy that can convert the water to steam. Okay, Rachel, how is your progress? Which question are you doing now?
57.
57. Okay. I'll show you the working on your drawing board. This is the working. So Rachel, what happened is you need to find the energy like gained by the water when it changed temperature from 60 degrees Celsius to 100 degrees Celsius. It is only 80,000 joules. And then for the copper to decrease temperature from 500 degrees Celsius to 100 degrees Celsius, this is the amount of energy. So this amount of energy is more than this. So there are 240,000 joules of energy is like extra and excess energy. Okay, so that this energy is used to convert water to steam. Convert water to steam. Okay, understand? Rachel, do you have any question? Can understand? So you are doing 58 now.
Yeah.
Okay. Chloe, are you doing question 58 now? Okay.
Yeah.
Okay. Chloe and Rachel, I have pasted the working on your drawing board. You can take a look of the working. So for question 58, the ice will gain energy to melt first, then increase in temperature. Okay, and the water will provide energy or will lose energy to the ice. So you have to find the energy required in order for the ice to melt first. Then is a change in temperature part. The ice only change temperature after it has been completely completely melted. Okay. Okay, so in 2 minutes time, I'm going to start electricity topic. Okay, so can we look at the DC circuit worksheet now? Are you all ready? Okay, I'll collect the drawing board and I'll do this now. Okay, class, now let's look at the DC circuit worksheet. I know we finished at question 5A last week, right? We finished at question 5A last week, right? Remember this worksheet? It looks like this. Electricity. So this worksheet covers questions on current electricity as well as DC circuit. Okay, it covers questions on current electricity and the DC circuit, the two topics. Okay, so we have done until question 5A. Okay, we have done question 5A. For question 5B, right, we'll skip for now. We'll talk about the concept on transformer. Okay, we'll talk about the concept of transformer later. Okay, it's related to transformer. Okay, we don't do it now. Okay, it's related to transformer. Let's look at question. We'll do a quick revision on the concept first. Then I'll talk about we'll discuss about question 6. So class. So if we have two resistors, okay, connected together in series and parallel, I have 2R, identical. Okay, what is the effective resistance for this? The top one, connected in parallel. What is the effective resistance? Like each one of them is R. Let me pick someone to answer the question. Okay, Chloe. Chloe, can you mute yourself? Don't mute yourself. Yeah. What is the effective resistance if there are two resistors connected in parallel? Each one is of R as a resistance. It is equals to
1 over R
plus
1 over R.
and this, right? So it's
Yeah,
2 over R to the power of -1 is R over 2. Okay, it is R over 2. Okay, good. So my question is, if we have, okay, a lot of R. Thank you, Chloe. You answered the question very well. Okay, so if we have a lot of R connected in parallel, what will happen? What about this case? Each one is R. I have N resistor of R each, okay, connected in parallel. What is the effective resistance? Anyone knows? Anyone knows the answer? Okay, Jonathan, please.
R over N.
Very good, excellent. R over N. Very good, R over N. Okay, class, please take note. This is a very important formula for you to remember. Thank you. Okay, the condition is you have N identical resistors connected in parallel. The overall effective resistance is R over N. Very good, okay, very good. Okay, so if we have R resistors connected in series, okay, continue in series, then N resistors connected in series. What is the effective resistance? Anyone? This is an easier question compared to just now the question. Can I hear from Gareth? Gareth, what is the effective resistance if I have N resistors connected together? Now the number of resistors is N.
N times R.
N times R. Thank you. Very good. Okay. So take note of this. Okay. So the more resistors we have connected in parallel, the smaller the effective resistance. Okay. If we have more resistors connected in series, the greater the effective resistance. Okay. So basically I can say, well, N increase here, R effective will decrease. For this case, if R increase, the R effective will increase. Okay, so take note of that. It's an important formula. Okay, okay, now let's look at question 6. Question 6, I want you to use potential divider idea. It's a potential divider idea. Okay, how do we find the V here? How do we find the V here? We shall use the total. Okay, V over 750 ohm equals to the total times, okay, 500 plus 700 as the denominator. Numerator is 750. You shall use this formula. Okay, so you can get the answer as 7.2 volts. So class, this is the potential divider concept. Okay, so the formula is, I call this R1, this R2, V1, V2. Okay, so this is R2, this is R1. So V1 equals to total V times R1 over R1 plus R2. What about V2? What about V2? I still want you to use a potential divider concept. Okay. What about V2? What's the expression? I'll choose someone to answer. Gareth, you are the lucky one. So what is the formula for V2? Use the potential divider concept. V1 equals to R1 divided by R1 plus R2 times V. What about V2? V times R2.
R2 over R1 plus R2.
Yes, very good. Okay. Okay, class, these two are used the concept of potential divider. Please copy down if you are not very sure. Thank you, Gareth. Okay, please copy down if you are not very sure. Okay, for part B, right? Part B, there are actually two questions. One question is, what happened to the resistance of LDR? First part. Second part is, what happened to the reading of voltmeter? Okay, so when the temperature of, the light intensity decreases, what happened to the RLDR? It's become darker, intensity decreases. For LDR, if the light intensity of the room decreases, what happened to the resistance of it? basically it's either increase or decrease, right? Does it increase or decrease? Jonathan, please. If the light intensity in the room decreases, what happened to the resistance of LDR?
Decreases.
Does it decrease?
Wait, intensity.
Intensity decrease. It becomes darker. The room is darker. So
the resistance increases.
Yes, increases. Okay, please remember this. Okay, increases. So what happened to the potential difference across it? Look at the potential.
Decrease.
Increase as well. Thank you. PD. Thank you. PD will increase. Okay. So basically it implies the voltmeter reading increase. Thank you. Rachel, okay so far. Any question? Can understand? Okay, thank you. Okay, now we look at question 7. Okay. What is meant by potential difference? What's the definition? So for physics, right, if we see what is meant by those questions on what is meant by, we always ask for the definition. Okay. We always look for the definition, right? What's the definition of potential difference? What's the definition of potential difference? Chloe, do you remember the definition?
Work done in moving one coulomb of charge from one point to another.
I hear keywords like work done. Good. Work done in driving one unit charge. Then
from one point to another.
okay, so we can say across 2 points, okay, of an electrical circuit. Okay, good. Thank you. Good. Okay, that's a definition. What is meant by potential difference? It is a work done in driving a unit charge across 2 points of an electric circuit. Okay. Okay, so for the second part, describe the function of a potentiometer. What's the function? I think we haven't given you the phrase yet. Anyone of you have read from textbook or other resources and you know the definition, you know the function? Anyone want to try? Anyone want to try? Anyone want to try? Gareth, you want to try?
Is it measures the potential difference?
Measures, not exactly. Okay, never mind. Thank you for your effort. I'll give you the definition here. Okay, it is used to, okay, this is A, can I put on top? Okay, this is the answer for question 7 part B. Okay, please take note. Potentiometer, right, is used to divide the output voltage in any desired ratio from the input voltage or a power source. Okay, so next part we are going to draw the circuit. The idea is about a full range, right? Full range from 0 to maximum voltage available from the cell. So we shall use potentiometer concept, right? So how do we draw the connection? Class, I'll give you the small drawing board. Then you can do on the small drawing board and show me the answer. I just hand out the small drawing board. You do on your paper, take a photo and upload. Perfect, Chloe did a good job. The rest of you, please take a photo and upload your diagram. Take a photo and upload your diagram, please, for question 7, part C. Oh, okay. Gareth, yours is okay. Good. Oh, hold on. Gareth, sorry. I think you won't get 0 leh. Gareth, because you put the voltmeter here, right? You won't get 0. No matter what, there's potential difference. I think you can put the voltmeter here. This part of the wire shouldn't be there. Gareth, you may want to try again. I think this is not really correct. Jonathan, how come yours is only like I think it's incomplete. Like it's like loose connection, right? Rachel, please have you tried the question?
Yeah.
Yeah, take a photo of your working. Class, I'm going to show you the answer in a short while. I think so far I see perfect answer from Chloe, and I'm still waiting for Rachel's drawing. Rachel, I don't think it is correct because your drawing will have 0 reading. Voltmeter must have some reading. Rachel, do you see in this connection somehow because there's some resistance value here, right? So the voltmeter reading equals to current times R. So it will not be 0 at all. Okay, class, I'll collect back the drawing board. I'm going to show you. You can see this one. This is the answer. So the key idea is you need to make sure it will vary from 0 to maximum voltage. So if this jockey is at this particular point, okay, at here the voltmeter reading is 0 because it will become short circuited. The current flow like through this part, there's no current on here. Okay, the jockey is here. If the jockey is on top, I'm going to use another color. The other color, if the jockey is here, like connected here, then this is going to give you V motor. The voltmeter reading will be maximum. Okay, so it's either 0 or between 0 and the maximum when you move the jockey around. Okay, let me repeat. When you move the jockey around, the reading of the voltmeter will change from 0, vary from 0 all the way to Vmax. So far, Chloe did a very good job. Her answer is perfect. The rest of you may want to take a look. I think Jonathan understanding is there, but your jockey is not fully connected to the circuit. Okay, so after change the answer, please raise your hand. Are we ready for question 8, class? Are we ready for question 8? If you are ready, raise your hand. Thank you, Gareth. Are we all ready for question 8? Thank you. Thank you, Rachel. Thank you, Chloe. Jonathan, are you ready for question 8? Thank you. Okay, so what is Ohm's law? Ohm's law is a very popular question in exam. Okay, you are oftenly tested on that. Okay, so may I get someone to tell me what is Ohm's law? Okay, Chloe, please.
Ohm's law states that the current flowing through an ohmic conductor is directly proportional to the potential difference across its ends, provided that its temperature and other physical conditions remain constant.
Very good. Her answer is excellent. Very good. Okay, I'm going to give you the definition now in case you are not sure what are the keywords to include. Okay, so on my drawing board, I just pasted here. Okay, Ohm's law states that the current flowing through a circuit is directly proportional. Okay, you must either mention metallic conductor or ohmic conductor. Chloe mentioned ohmic conductor. We also accept metallic conductor. Okay, it's either metallic or ohmic conductor. Directly proportional, keywords directly proportional to potential difference cross. And somehow you have to talk about, given that the physical conditions such as temperature is constant. Most likely it's a 1 mark question. Okay. Okay, now I'm going to let you try question 8, part B. Question 8, part B. Okay, I just handed out the small drawing board. Please sketch the curve and then use pencil. Okay, class, for physics question as well as math questions, please always use pencil to sketch. Use pencil. Okay, and this is going to be a curve, not a straight line. Okay, don't draw straight line, use curve. Draw a curve. Please take note, filament lamp is not an ohmic conductor. It's not ohmic conductor. A filament is not an ohmic conductor, so we don't expect a straight line. If it's a straight line, it is strictly a ohmic conductor or metallic conductor. Gareth did a very good job. Chloe, well done. Jonathan, please upload your working. Rachel, also please upload your working. Yes.
May I use the toilet?
Oh, sure, go ahead.
Thank you.
Okay, well done, Rachel. Oh, Rachel, you may want to extend a bit more. In general, the shape is okay. Rachel, the final voltage, right? Is it not very, I mean, for the time being, right, the final voltage is not very clear. So you'll need to show that the final voltage is going to be like 3. Okay. Okay, good. Jonathan, can you upload your working for the curve for question 8 part B? If everybody got the correct answer, I will not go through. We'll continue. Okay, we'll continue. We have a few more questions, and I think we can start practical electricity today, the new topic. I try to teach slightly faster than your school, okay, either about one topic in advance. So when your school teacher teach you, you can understand the concept well, okay? So you can focus more on those techniques in exam, like what are the keywords you need to include, how do you phrase the answer, those are details, okay? Those are exam skills. Sorry, Jonathan, can you upload your working for 8B, the sketching? Okay, thank you. Can I get someone to explain the diagram? Okay, maybe I get Chloe. Chloe, can you explain to us your diagram? Yours is perfectly well done. So can you explain to us? Like first of all, what's the shape? And then I'm more interested in this point. Because it's not metallic conductor. Okay, so cannot draw straight line, right? Not metallic conductor, so we cannot draw straight line. So as current increases, what happened to resistance? Increases as well. Okay, so like at this particular point, some of you actually show a very nice, actually all of you show a very nice shape, but not every one of you given this point 18.0 and 3.0. Can you explain to me why this graph passing through this point?
Because the question said so.
Yes, because the question clearly stated that you have to show the shape, right? So you need to, thank you, Chloe. So you need to make sure, class, you need to make sure your graph passing through this point as a final point. Okay, you cannot have the graph like halfway and like that. Shape is okay, but we don't accept the answer. Okay, this is not acceptable. Understand? Okay, thank you, everyone. We'll continue with next part now. Okay. Semiconductor diode. Okay, diode, this is the symbol. The next part is on semiconductor diode. This is the symbol of it. So the current can only flow in one direction. Okay, not the other one direction. The other direction current cannot flow. So as current increase, the resistance will decrease. So the current over V ratio will increase. Okay, so for question 8 part C, your graph should look like this. And this region is called what region? You remember there's a name for this region. Okay, I'm going to complete the whole graph. I'll draw a little bit more. You are expected to draw this. This is already perfect answer for the question. But if you want to draw a little bit more, something like this, milliampere here. After that is breakdown. Okay, the device breakdown. So for this region, class, for this region, what's a name for it? For this region, we call what region? This region we call what? Rachel, do you remember what do we call this region as? The choice is forward bias or reverse bias. This region. Is it called forward bias or reverse bias?
Forward.
Yes, this is part called forward bias. Okay, then here is called reverse bias. Okay, forward bias is like the current flow in the normal way. Okay, thank you, Rachel. Okay. Normal way is forward bias. If it's the other way, then it's reverse bias. Okay. The reason I revised about forward bias and reverse bias in question 8 because question 9, you need that information in your explanation. Okay. You need this in the explanation in question 9. Question 9, you see diode, right? This is semiconductor diode. Okay. So in diagram 1, when the switch is closed, state what happened to the bulb. In diagram 1, that's when the switch is closed. State what happened to the bulb. Okay, Rachel, you are the lucky one. Okay, okay, yeah. So Rachel, can you tell me what happened to the bulb? When I switch the close, what happened? When I switch, when I close the switch, what happened?
Light up.
Yes, very good. Simple and elegant. Just say light up, or just say it lights up. Okay, good. Okay, Rachel, you help me to choose another student. You can put your mouse over this part, this bar. Then you can, I authorize you already. You can play the slot machine to choose another student.
What if I choose myself?
Then you can choose again. Okay, Chloe. Thank you, Rachel. Okay, Chloe. Then, how do you explain your answer for part 2?
I just said that current can flow from through the diode without getting.
Yeah, so we talk about forward bias, reverse bias. What kind of keywords you want to use?
Forward bias.
Very good. Okay, forward bias. Okay, so for question 9, you just can say diode. Okay, you need to talk about the diode. The diode is forward biased. Okay, forward biased. This actually will give you 1 credit. Okay, the key words here is forward biased. Okay, they give you 1 credit, and you can talk about it allows current to flow. Okay, thank you. So it allows current to flow. So plus it allows current to flow in the circuit. Okay. Thank you. And for part B, right, what type of behavior is displayed? by the diode in diagram 2. Now the current want to flow like from positive terminal, but it seems cannot, right? What do we call this as? Let me draw someone. Gareth, what kind of behavior it is called?
Insulator.
Insulator. Can we say reverse bias instead? I think you understand the concept. It become a, but we don't say insulator. We say it's forward bias, reverse bias. Okay, thank you. Okay, reverse bias because it's a diode, right? Explain your answer. Okay, so here is the explanation. I'm going to show you the answer.
Just about 9, but after
Okay. Sorry, I need to clear back this drawing board first. Okay. Sorry, let me try again. Seems I cannot copy and paste my answer. Okay. On the mind, just right here. Okay, explain your answer when the switch is closed. When the switch is closed, bulb doesn't light up. Does not light up. Okay, this is one mark. And the second mark is because the diode, you shall say the diode prevents the current, just use I, current from flowing through. Okay, that's all. This is the second mark. Okay. So what are the keywords? What are the keywords? For part 2, the keywords is mainly on prevent, the diode prevent the current from flowing through. Okay, that's all. Okay, now let's look at part C for question 9. Okay, class, part C, right, is not exactly in your syllabus. It's a higher order question. So they may give you as a data response question. Okay, they may give you as a data response question. You know, for paper 2, section B, there's one long question as a data response. They may give you some description of how does this work. Okay, so I'm going to show you how does the current flow. So who can still remember if you see this sign, right? What does it mean? Anyone of you can still remember? Any volunteer? What does this mean? The input is what? Jonathan, do you remember? The input is what? See, the sinusoidal graph means what? Maybe we try Jonathan. Sorry, Gareth. Gareth, do you remember? If you see this, what does it mean? This sinusoidal graph sign.
You see an AC or something.
Yes, it's an AC source. Thank you. Okay. What does AC mean? So when we say AC, right? AC stands for alternating current. Okay. Alternating current. So it means sometimes the current flow in this way. Okay. Sometimes current flow in the other way. Okay. Sometimes current flow in the other way. So let's say current flow in the blue color direction, right? In this direction. Come to this junction, can the current go up? Cannot, right? Current go up, cannot go up. So current only go this way. Current go this. Then can current go up here? Also cannot. So I'll show you the path of the current. Okay, then go this way. Then the current flow back to the other terminal. This is one path. Okay, one path. And there's another possibility is the current flow in the orange direction. Okay, can go this way, but not the other way. Go like this. Here cannot go through, right? Here cannot go through because reverse bias class, reverse bias. Okay, then the current flow like that. Coming out this way. Okay. And you may notice in both cases, the current flow from top to the bottom. Okay. So what type of circuit? Okay, class, this is something you need to remember. This is actually called a full wave. Full wave rectification circuit. As I mentioned, it's not stated in your syllabus, but I think school exam highly possible give you such questions. And they will make it as a data response question, as a higher order thinking question. Okay. And then what is the name of the arrangement of the 4 diode in the circuit? It's called bridge rectifier. Okay. So class, I'm trying to teach you something of higher order thinking. Okay. So full wave rectification circuit, and it's called bridge rectifier. Okay. For the time being, we'll skip part C, part 3. Okay, you haven't really learned the wave yet. We'll cover this again under the topic EMI, electromagnetic induction, which is our last topic. Okay, we'll cover this in the last topic, electromagnetic induction. Okay. Okay, so but we'll answer the last part. What is the function of the 4 diodes in the circuit? What's the function of the 4 diode? Okay. Okay, so you can say it make the current flow through resistor X in one direction. Okay. Okay. Sorry, I go back to the previous part. Do you see? No matter the current flow in which direction from the source, right? It is always from top go down. Blue color or orange color, both cases, the current actually flow from top to bottom. That's what we mean by flow in one direction only. Okay, flow in one direction only. So that therefore, okay, here. Okay, this is the answer that you can write down. Okay, make current flow through the resistor X in one direction. Okay. Okay, in one direction. Okay, so for question 10, right? Question 10, you can do the question as if it's a wave question. Try to do this question as a wave question. All of us have learned wave. Okay, all of us have learned wave, so you can do the question as a wave question. I think we probably don't have so much time to finish question 10, 11. 10 and 11 are not very tough. I'll say the tougher question is question 9. Okay, because we don't really cover so much diode in our main syllabus. Okay, especially the full wave rectification, the bridge rectifier circuit. Okay, take note, this is a general knowledge for you to understand. Okay, so let us try at least part A lah, for question 10. So when we look at the peak, voltage, right, we are looking at in the y direction. In the y direction. Okay, so this is y gain. And it is 6.0 volts per cm. So there are 1, 2, 3. How do you find the peak voltage? You can say peak voltage equals to 6.0 times 3, which is 18 volts. Okay, so we follow 2SF. And then second part is supposed to find what is the period of the voltage. Okay, period of the voltage. Okay, and then we should look at the time base, 20 millisecond per cm. Milli is 10 times 10 to the power of negative 3. Okay, 10 to the power of negative 3. Okay, so we can find the period equals to 1, 2, 3, 4, 5, 6. Okay, did I miscount it? Oh, okay, I think my method not very good. Okay, let's count like this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So basically 1.5 period. Okay, because you can see half 1.5. 1.5 period equals to 10 multiplied by 20 times 10 to the power of negative 3. Okay, then I can do calculation. I can get 1.5 period equals to 0.2 second. So period equals to 0.2 divided by 1.5, which is 0.133 millisecond. So the skill here is, in case you don't have a very nice, like, I don't know how to read this lah. So instead of reading one wavelength, right, I look at 1.5 wavelengths, which is correspond to 1.5 period. Okay, what is the time? Okay, so that's how it works. Okay, so this is the final answer. Okay, so for homework today, I want you to finish up this worksheet. Let me write down here. Question 10, question 11, question 10 and 11. Homework is question 10 and the question 11 of the worksheet on electricity. And next week, right, we will be starting practical electricity. Okay, we'll be starting practical electricity. I have uploaded the notes and the worksheets, everything on the class chat. Notes are already available on class chat. Okay, so when you have time, you can download, print out, and read through. Okay, so that's all for the lesson today. Okay, I'll see you next week. Thank you, everyone. Please remember to finish question 10 and 11. Okay, homework is question 10 and 11 of this worksheet. Okay, thank you. See you next week. Okay, bye-bye.